Okay, so this chapter is about these things. Okay, now actually before I go on, I got to remind myself to tell you, for those who are going to register for this course, please hang in your homework problems on time. Okay? On time means that all the due dates have been posted on the Blackboard, and on time means that okay, if I think for today's homework problems, it will be due on next Tuesday, right? Okay, so September 9th. So September 9th, when I give the lecture here, by 5:30, your homework problems are due here, and then we'll give the homework problems to the TA. So please hang in your homework problems on time. Now, for those who actually just sit in, if you also want to hang in your homework problems, you are welcome. um, Now, if you don't hang in your homework problems on time, then the TA does not need to grade your homework problems. Okay, and then you lose points. And then then after that, don't cry. I strongly, of course, encourage you to really work on the homework problems because exams will be from the homework problems. I mean, okay, not going to be exact, but if you understand what's going on of those homework problems, then you will have a better understanding of where and how the exams will be given. So that's important. Okay? And then you also, when you do homework problems, you will ask questions. You will be able to ask questions, and that's important as well. Okay, let's start to talk about chapter 2 and chapter 3 for today's lecture. And feel free to stop me, if you have questions during my lecture, because this is important. And also, I'm not going to go through mathematical derivations. That's the whole reason why, and part of the reason why we're given the quiz at the very beginning, okay? Because you have to work out those mathematical derivations on the book, and that's really not the essential portion. I'm going to say, okay, I stand here and derive those things for you. I mean, okay, no, those things you can do that yourself. And my job here is really to explain what's going on, what's behind these equations, what's the meaning of these equations, what are the connections between these chapters. This is a textbook. It's, as I said, it's a more than a 900-page textbook. If you read every chapter, you say, oh, yes, it's well written. But there is still actually one subtle, I would call that problem. It's simply because it's very difficult to connect the knowledge between these chapters. Why are we teaching chapter 2, chapter 3, and it doesn't seem to have a lot to do with the actual imaging. But in fact, everything is connected. Okay, and that's why some of these students actually from past years, okay, they still sit in, they still want to hear this again. And as I said, if you really want to learn MR, you have to go through this like 3 times. Then you really have a solid understanding, or say a better understanding of what's going on. Okay? And after this course, actually, I heard Dr. Hickey's talk. I think he was very enthusiastic, and he told you guys, he said, okay, after this, you will be able to do research. I will add one word in his sentence. I will just say, after this course, you will be able to start to work on research. You will be able to start to actually read some papers, and you will still have tons of questions, and you will still ask questions, and you still come back and say, oh, what's going on, with all these fundamental, say, equations or knowledge there, concepts. Okay? So that's where that's what I'm going to go through in this course. Okay, so here are the important, say, concepts in this chapter. Okay, and I made actually there are 6 bullets here. So we are going to talk about equation of motion. That's the Bloch equation. That's the most important one. Okay, throughout actually this entire MRI knowledge, or say course. Now, so in this chapter, we just learned the simple one, the most basic one. Okay, and then we'll talk about what is phase, and you will see that actually after we solve the Bloch equation. Okay, we'll see where this Lamma equation is from. we'll see what different way to solve the this Bloch equation. Okay, so there's a complex way to solve the problem. And then what's the meaning of the word precession? And then there's also this terminology, gyromagnetic ratio, gamma, or actually gamma bar. We call that gamma bar, which is defined by gamma divided by 2 pi. Okay, so to start with, okay, we'll talk about this magnetic force. Okay, now but before we go into any details, the first equation actually you see is actually this one at the bottom. Okay, so you can look at either screen. And this just represents the differential force in terms of mathematical meaning. That's just a differential force. And this represents the current. This is the small section of a piece of wire. Okay, it doesn't show on this figure, but the L here just tells you this is a small section, and it carries actually a vector. Okay, so this is probably not easy to see on this PowerPoint slide, even though I use bold. But this just tells you, okay, you have a small section here and it's a vector, it's pointing to the tangential direction of this loop. Okay, same thing for that guy. And so this is actually the definition you have learned in, say, freshman physics course. Okay? So this is a basic definition of force. So we consider every differential force at every section of the loop. And then so how do we calculate this? All right, so then you say, okay, you raise your right hand, right? And then you have the small section DL going this way, you have B field going that way, then you do a cross product. Okay, for example, this guy doing this gives you actually differential force this way. I think you're asking whether I want to record the class. You can just say no. Okay, so so first thing is that you say, okay, you figure out what is this differential force, right? So if you go through the textbook, I mean the derivation. I think I'm loud enough. Yishan, you can hear me, right? No problem, right? Yeah, right. The voice part can even bounce back to me.
Hello.
I don't worry about that.
Their battery's out anyways.
It doesn't matter. I mean, this, we don't have too many people. So okay, so back to here. The first thing is that you say from the mathematical formula, and you have to figure out what is the equation of this side, and then so basically then you write down the differential equation. Okay, now it's a little bit complicated just because you got two vectors here, and these guys actually, this guy, of course, is a function of space, and this guy, of course, in this case actually, okay, you say it's just a B field pointing to a z direction. Okay, but in the next example, you will see actually this guy, of course, can also be a function of space, and also if you want, actually, make this a function in time. Okay, and so it's just a little. You just have to be a little bit careful to write down these things. But if you have simple geometry like a circle, okay, in both cases you have a circle, or I think, I think in this chapter you also see a square loop, right? For simple geometry, you can actually write down these things without a big problem. Okay. Now, of course, if I give you an elliptical loop, then you probably start to scratch your head, say, "Oh, okay, then you need more time." Okay, I don't think we will bother you with that during the exam. Okay, so once you write that down, then of course you can say, okay, now I want to calculate the total force. Okay, a closed loop. Now, so you say, okay, you just do the integral, and then this guy actually, if you have, so this is the equation. So if you have actually a constant B field, then you just pull this outside your integral. So then you got a minus sign just because I switch the cross product, right? And then so basically we have this, and then you integrate over the entire loop. That of course gives you 0, so the whole thing becomes 0. Okay, so the total force on a closed loop actually is 0. Now, but again, if you just want to see this, of course, in a more visual way, then you say, well, okay, I really figured out what's the differential force at each section, right? So in this one, it looks like this. Well, so actually for this point, this differential force is pointing this way, but for a point opposite in the opposite direction, and there it's pointing to the opposite direction. So you can imagine, and that's true for every point on this loop. So if you go through the whole thing, then you get the 0 force.
Can't hear you in the studio to record.
Yeah.
Try the light
set the battery may not out. Okay, so and then same thing here. Okay, so you can go through that yourself and say, well, okay, convince yourself. Say, okay, even just from a visual way, your total force of a closed loop is 0. Okay, so this is a trivial thing. But the force is not the only thing actually we worry here. Okay, what we have to worry about is actually the torque. Okay, now why we worry about torque? Okay, now just 5-10 minutes later, I will tell you why we have to worry about torque. But
Can I ask you to put that on now? How far into your talk are you?
That's okay. Don't worry about it.
Okay. So just start recording from now.
Yeah, that's fine. They're also doing the recording. Yeah, thank you.
Okay.
Yeah. Like this. Okay, so yeah, is this too loud for you guys? Yeah, until I yell. Okay, so torque is actually important. Okay, so even in these two cases, so just before I show you the next slide, there is no net torque of this guy. Okay, but then there actually is a torque on that one. Okay, so how do we actually define torque? So the torque is defined this way. Again, the first thing is you have to figure out what is the differential torque at every section of your wire or your loop. And then it's defined by this R cross this differential force. And this R is basically just say, okay, where is the origin, right? And then to the position of that piece of wire. I mean, at that special location. So have this definition, and then again, well, okay, then the say a little bit tough part is that you have to write down what's the mathematical formula from this side, and then you integrate this whole thing, and then figure out what is the total torque of this exerted on a given loop. Okay, so these two bullets are just telling you that even though the net force is 0 on closed loops, well, but the torque may or may not be 0. So that's the that's the lesson. Okay, now of course if you do the calculations, then you will find that this torque is why one guy is 0, one guy is not 0. Okay, so if we go back, okay, now remember this definition. Okay, it's R cross df. All right, so let's go back. So let's just say again, if I just do a visual way, right, just very quickly, you look at this. So this is the center of the coordinate system, and then my R is just from this point. Say, okay, take this point, and R is just from this one pointing to this one, right? So if I do a cross product, R cross df is actually the normal component. Is in fact it's the normal to this loop. So R cross df in fact is 0. So that's true for every point on this loop. So your differential torque on this guy in fact is 0 at every point. And so of course when you add them up, of course the total torque is still 0. But it's not the case here, right? So again, if you say just take this point, so what's my vector R? My vector R goes this way, goes down, and then this differential force goes this way. So in fact I got a torque pointing out of the plane. Same thing to the opposite point. I have R there, and differential force going that way. Okay, again, use my right hand, and do the cross product, and find out my differential torque also moves out of the plane. Okay, so the net torque, in fact, for this system is pointing out of the plane. Okay, now this basically says, well, okay, so this loop is rotating. Remember, this loop is rotating on this YZ plane such that actually your torque is toward in the X direction. Now, of course, there's a question about whether it's counterclockwise or clockwise or counterclockwise, and then that gives you the sign of the torque. So you can figure that out. Okay, so the first line basically kind of shows what I said, but there's one subtlety. Okay, so this is a question, of course, when I go through this chapter 2 and ask myself, I say, okay, in this chapter, if you read it, it shows you the simple geometry, it shows you a simple example, it shows you, oh yeah, my net torque at the end, actually I will get that mu cross B. Okay, now what's mu? Okay, it's defined later, but before I get into that, I just want to say the first line, in fact, is true in general if you have actually a closed loop. At least, I just proved that actually myself. Several years ago, I proved that myself. I said, hey, can I just in general prove it? If I have a closed loop, then the torque at the end is really mu cross B. Okay? Yes, I can do that, but it's a little bit, I would say, difficult. You really have to use the Stokes theorem and really do a few mathematical tricks and figure that out. Okay, but again, that's not going to be an exam, so don't worry about it. All right, so then what's mu? Okay, so why do we write torque equals to this mu cross B? Okay, so this mu, in fact, is the important one in MR. Okay, mu is actually the magnetic moment of, say, a current loop. In fact, or actually, it's magnetic moment of an atom. And for that atom, we just assume that, okay, if that atom in a classical picture, if I have this atom, circulating a loop, then that gives me a current, and that current multiplied by the cross section, meaning that the area of the loop, that gives me actually the magnetic moment. Okay, but again, this is a classical picture. So that's kind of the classical definition of this magnetic moment of a current loop, or actually in MR, this magnetic moment is the, as I said, this mu is the magnetic moment of an atom. So now I kind of introduce you this magnetic moment mu, and then because it involves with the current, okay, so now you probably can believe what I just told you, why that torque, and at the end you can write that in terms of mu cross B, okay, because mu by definition is this guy, and this involves current and involves the geometry of your loop. And by the earlier definition, the differential torque is actually equals to R cross product with the differential force. Okay, so those things actually also have the geometry involved, and also of course the current is involved. Okay, so that's why at the end we can actually really write down that equation. All right, but for you guys right now, you just assume, okay, you know that your torque is equals to mu cross B. So all right, so now this kind of just repeat. Now this is actually an example in the textbook. Okay, so this kind of just gives us a repeat of what I said. So if you have a B field, which in fact pointing to the, which is this, in this case, which is the pointing to this direction. Okay, so you have a Z component and also a Y component, and here's the angle theta, and you place your loop just actually on the XY plane, and so then you can write down, say, what is the raw direction, right? That's the radial direction. And what is the phi direction? Phi direction is the tangential direction of the loop. Okay? And then by all those definitions, so remember again, your differential
torque is equals to that R cross product with a dF, and then dF, again, you can write that in terms of this IDL cross B. All right, so you spell out everything, and then you're going to obtain this equation. Okay, and then after this, now this is actually the phi direction. Okay, so this is the phi direction, so it's this guy. And but then you have to, of course, break this in terms of Cartesian coordinates, and then you integrate the whole thing over this d phi and figure out, oh, what's the torque? The torque is actually this guy pointing to the x direction. Okay, but then on the other hand, you say, well, okay, does this agree with mu cross B? You know, so that's actually the lesson from this little section, right? So you look at it, you say, oh, what is mu? This magnetic moment in this case. Okay, so we said mu is actually the current I multiplied with this area. But then you also actually have a vector. That vector is pointing to the z direction. So what is mu in this case? Well, that is I, right, times pi r squared, and then it's pointing to the z direction. Now if I do a cross product with mu with the B field, then I'm sorry, actually, pointing. The mu is pointing to a z direction, right? So then this term is gone, and then I only have this term left. So that's where I get this sine theta, and the direction is, the final direction, in fact, is pointing to the negative x direction. So that's just what you have to figure out through this math. Okay. And so this just gives you an example and say, well, okay, this little example kind of convinces you at the end, your torque is really mu cross B. Okay. So any question up to this point? Okay, and then I think I don't remember, which homework problem actually asked you to calculate this guy, and this is a different homework problem. Okay, so then now we spend a lot of time to talk about the torque. And then what's going on? Why are we talking about these things? Well, because the end goal, okay, so I have to tell you what's the end goal. The end goal is actually to derive the Bloch equation. Okay, so in order to derive the Bloch equation, we actually need 3 equations. Okay? And so in the next, or probably not the next slide, but in the next slide, I'm going to show you what 3 equations we need. Okay, so that equation for the torque is the first equation. Okay, so let me just not say the first equation. Let me just say one of the 3 equations we need. So that is one equation. Second equation we will need is actually that guy. Okay, but anyway, we have to start with the angular momentum, which is called J. And again, from the freshman physics, okay, you learn that the angular momentum. So I have a moving object, say, going this way, for example, and by definition, the angular momentum J is equals to R cross P, and P is the linear momentum, okay, which is defined by m times v. M is the mass of the object, v is the velocity of the object. Again, all those guys actually have the vectors there. So by definition, my angular momentum is like that. Okay, so now if you consider what is the derivative of my angular momentum respect to time, then you can do this calculation. In fact, this is homework problem 2.3. Okay, so you just say, okay, by definition, J is R cross P. Put in there, the first term is dr dt cross mv. mv is my P. Okay, plus R cross dp dt. Okay, the first term is 0 because dr dt by definition is my velocity again. So the cross product of the same vector, v cross mv, of course that's 0. So you only have second term left. And by definition, this dp dt, the change of the linear momentum as a function of time, we say with respect to time, that actually is the force. That's by definition from physics. So then at the end, I have R cross F. R cross F, in fact, gives me the torque. Okay. So that's the second equation we need in order to derive the Bloch equation. So we have dj dt equals to torque. Okay. Now the third equation we need is actually this guy. It's a relation between the magnetic moment and the angular momentum. Okay. Now this actually is the quantum mechanics we're talking about here. Okay, because as I mentioned to you several minutes ago, this mu is the magnetic moment of an atom. So experimentally, actually, people measure the magnetic moment of an atom or electron. But then you say, well, okay, how do we figure out J, or in terms of the angular momentum? So in quantum mechanics, this angular momentum J is now it depends on actually what system we're talking about. But let's say if I just have one proton, then this J in fact is just half divided by Planck constant, okay, the h bar. So okay, so on one side actually you have that, and this side you measure it, and the relation is basically linked by this coefficient gamma, and that gamma is, we call that gyromagnetic ratio. Okay, so now I have to be a little bit careful here. I have to also, of course, warn you here. This gamma here, okay, even though I wrote gyromagnetic ratio, but this is really the gamma we're talking about, the gamma you see in the book. But normally we don't use gamma. Normally we use gamma bar, because we just take that gamma divided by 2 pi. So you see that next line we have this gamma divided by 2 pi. This is gamma bar, okay, and it's very difficult to show that in Microsoft. So when I write gamma, so this is what I'm writing, right? So you see, oh, it's a big number, and the unit is actually radian per second per Tesla. Okay? So, but then when I write this in terms of gamma bar, the number is 42.58 megahertz per Tesla. Okay? And so now, of course, if you have been using this number for a while, I mean, for any calculation, then this number, in fact, you will remember pretty well, even down to the total of 4 digits. Okay, so now if you don't remember, you say, well, okay, roughly what's gamma bar? Okay, roughly it's actually 42 megahertz. Okay, 42, 43 megahertz. So when you hear people say at 1.5 Tesla, what is the frequency of that magnet at 1.5 Tesla? Well, typically people may say 63 megahertz or 64 megahertz. Okay, so if you just consider gamma bar as 42 megahertz per Tesla times 1.5, right, multiplied by 2/3. Oh no, sorry, actually 3/2. Then the answer is what? The answer is actually 63. Okay, so that's where the 63, 64 megahertz for 1.5 Tesla is from. If we are looking at 3 Tesla, then of course you double that number, 63 times 2, you get 126. Okay, 64 times 2, you get 128. So 126 to 128 megahertz. So that's pretty for 3T. So that's why you are hearing people say, oh, 126 megahertz, 128 megahertz for 3 Tesla. So that's actually from that number. Okay, so it's a gyromagnetic ratio. Okay, and then the last bullet is about, say, okay, from the classical picture. So that's I don't remember whether you get that homework problem or not. But anyway, that homework problem basically says, okay, now let's look at this gyromagnetic ratio from a classical picture. Okay, so then from a classical picture, in fact, because we already said what's the definition of mu, right? Okay, definition of mu in the classical picture is you have the current, you have the loop, so it's I times this area A. So that's a classical picture for that guy. Okay, and then your angular momentum by definition is R cross P. Okay, so again, if you have a loop, you have a you have a moving, say, proton or electron, then you can figure out what is the angular momentum. All right, so then you cancel out certain variables, and then you will find that, oh, this gyromagnetic ratio gamma is actually equals to Q divided by 2m. Q is, in fact, is the charge of your proton or the charge of your electron. And if you take this number, you do a calculation, actually you will find that this number turns out to be pretty close to this number. I mean, pretty close means that, pretty much actually the same order of magnitude. Okay, so that's actually, to physicists at the very beginning, actually this is important because in physics, the first thing is that when you do any calculation, make sure your sign is right. Okay, that's the first thing. Second thing is that make sure your number is actually correct to the order of magnitude. Okay, and then the third thing is you say, well, okay, then let's look for the accuracy and precision, and then so bring the number within 10%, 20%, 30%, something like that. Okay, so this is actually how any physicist actually should work. Okay, now just quickly ask you, do I go too fast? I guess, I hope not. All right. Okay, so before we actually really show you this Bloch equation, all right, so there is another comment actually in the book, and I have to talk about this. Basically, it's a remark about the electron imaging. Okay, so the first bullet basically says, well, okay, if you, based on that previous equation, okay, so this classical picture here gives you, say, oh, okay, what is the, from the classical picture, what is the gyromagnetic ratio, right? It's about this. All right, so then the next thing is you say, well, then if we want to do electron imaging, well, then what kind of gyromagnetic ratio would be? So if you just consider the ratio of the mass, and the ratio of the mass between a proton and an electron is about 2000, 1836, and it just tells you that, oh, the gyromagnetic ratio of an electron is 1,000 times higher than the gyromagnetic ratio of a proton. And now from the measurements, actually, you get a number like that. Okay, but anyway, that's still on the order of 1,000. So then here's the question. You say, okay, in MRI, we always do the proton imaging. Well, not always, sorry. Actually, most of the time we are doing the proton imaging. Okay, of course, we are doing some imaging of other nuclei. But how about electron imaging? Okay, so that's actually that little paragraph in the textbook is about. Okay, now I have to warn you here. Okay, so in the second edition, actually, we fixed that paragraph. Okay, in the first edition, actually, that paragraph has a problem. Okay, the reason actually it's difficult to do electron imaging. There are two major reasons. Okay, and in fact, you can realize that very quickly. First one is because of the gyromagnetic ratio is so high, so large for electron. So if you say, okay, I also want to design a Tesla magnet, I mean a magnet with Tesla field strength, and then I want to do electron imaging, well, guess what? All of a sudden, you are looking at the microwave range, meaning that your frequency is going to be in the microwave range. Okay, so right now, actually, I haven't told you the Lambda frequency, but basically that frequency, that gamma, you saw that gyromagnetic ratio, okay, it's 42.58 megahertz per Tesla. So if you say, okay, now you multiply that by 1,000, right? Because it tells you factor 1,000. So for electron imaging, then we are looking at 42 gigahertz per Tesla. Now, if you want a field strength of 1 Tesla, then you need a resonance frequency of 42 gigahertz. 42 gigahertz, that's in the microwave range. And now you want to design, say later in chapter 3, we're going to talk about the RF coil. You want to design such a coil to give you 42 gigahertz, and then you are able to actually put somebody in there without cooking that person, by the way. Then it's a lot of technical challenge. Okay, you all know actually how microwave will do to your food. Okay, so I don't need to tell you what will happen if you send some biological samples into a microwave oven. So that's one problem for the electron imaging. Okay, I'm not saying that people are not doing that. In fact, people are designing machines. So modern technology, in fact, has, really pushed the front end, and people are doing electron imaging. Okay, somebody, if I remember correctly, probably 5 years ago, or could even be almost a decade ago now, I think there was a paper which shows that how to design such an RF coil and have and add that microwave frequency and do the electron imaging. Okay, so people are trying to do that. Okay, so that's the first problem you have to solve. The other problem is actually by nature, you say, how many free electrons actually we have inside our body? Not too many. Okay, we have actually a lot of water protons, and these protons are kind of, say, free, but we don't have too many free electrons inside the body, because free electrons are free radicals. Free radicals are, guess what, are bad to our body. Okay, that's where actually the cancerous cells actually would have free electrons, free radicals. In fact, those are what they call. So we don't have too many free electrons or free radicals inside our bodies. So because of that, the abundance of free electrons are very, very low inside our body, and so then it becomes also very difficult to do electron imaging, because you are not going to have sufficient signal to noise ratio to do electron imaging. Okay, but a big giant magnetic ratio actually does help. Okay, right now you probably don't really understand why I say that. Okay, you have to, in order to understand the signal to noise ratio, that's chapter 15. So not until you really go through chapter 15, so that's like halfway mark of this book, you won't understand my remark here, why a big gamma would really help. A big giant magnetic ratio would really help your signal to noise ratio. Okay, so then, all right. Okay, so then I guess there are more stuff actually in this chapter. Say notes I have to tell you, and then so how about other nuclei imaging? Okay, yes, we can actually do those imaging in MRI with MRI. Okay, so you might have heard fluorescence imaging, you might have heard sodium imaging, you might have heard phosphorus imaging. Okay, so those are actually possible. And so what's the basis of these things? Okay, the basis is that the net spin or the net angular momentum cannot be zero. Okay, and so what do we mean? Okay, so it's not the say the total number of protons and neutrons we are looking at. In fact, it's the total number of protons we are going to look at. It's also the total number of the neutrons we are going to look at. Okay, now it's not that simple. You probably actually, for some complicated nuclei, you probably really have to check the some physics measurements and just check what is the net angular momentum of that specific nuclei. But here it just gives you an example. If you have oxygen 16 or if you have carbon 12, well, those guys, well, guess what? They have they have even number of protons, and they also have even number of neutrons, and such that actually the net spin, or say the net angular momentum from the proton side is zero. The net spin, or the net magnetic moment or angular momentum of neutrons in those species are also zero. So then at the end, you just have you don't have any angular momentum, or you don't have any magnetic moment left for those species, meaning that oxygen 16 or carbon 12. Okay, so you would never hear people say, oh, we are doing imaging on carbon 12. Okay, that's not possible, but you can do carbon 13. Okay, so there are some AMR on carbon 13. That's possible. But you can actually we can actually imagine nitrogen 14. Okay, nitrogen 14 contains 7 protons and 7 neutrons, and so then you got actually a non-zero, or let's just say a non-zero magnetic moment from the proton side. You also have a non-zero magnetic moment from the neutron side, and then these two guys actually they are having different quantum numbers, okay, meaning that one is from proton, the other guy is from neutron, so then the combination of these two still give you a non-zero angular momentum at the end. So nitrogen-14, in fact, has a non-zero angular momentum, so meaning that non-zero magnetic moment, and so then we can image it, that species if we want, if we have sufficient abundance. Okay, so the last remark is just kind of similar to what I told you about the electron imaging. Okay, so for all these gyromagnetic ratios for nuclei, okay, they have about the same order of magnitude. Okay, you can see that from table 2.1. Okay, but what makes the difference in terms of the signal to noise ratio at the end is really the abundance of each species. Okay, so in terms of abundances, actually there are two things. One is actually the natural abundance of each species. The other guy is actually the abundance inside our body. Okay, because that's what we are interested. Now, if you are interested in something else, then of course, then you have to see how much each species actually, how much the abundance is in that, say, material or object you're interested. Okay. And this table 2.1 actually you will encounter again actually when we are going to chapter 7. Okay, so now we are going to this finally. Okay, so I'm going to show you how this Bloch equation is going to be put together. I mean, going to be written down. So again, as I said, there are three important equations. Okay, one is your torque equals to mu cross B. That's the first guy. Second guy is the change of this your angular momentum as a function of time is also the torque. Okay. The third equation is the relation between the magnetic moment and the angular momentum. So mu equals to gamma J. Okay, so now, so with these three equations, how do we write down the Bloch equation like this? Well, okay, so if you look at this, d mu dt, well, and by the way, actually, this guy, of course, should be a vector, right? Okay, so d mu dt, then I will start from this guy. Okay, mu equals to gamma times J. So you put this guy in here, then I'm going to have gamma times dj dt. Okay, so dj dt is my torque. So basically, my d mu dt now equals to gamma times torque n. Okay, and torque n equals to mu cross b. So now actually write down this gamma mu cross b right away. So that's the Bloch equation. That's actually the simplest version of the Bloch equation. Okay. And then the next bullet is just to remind you, well, in fact, that's a homework problem. Just from this equation, you can prove that the magnitude of this magnetic moment, mu, in fact, is a constant. It does not change with the function of time. Okay. So that's the point of that homework problem. Okay, it doesn't say that, I know. Okay, in that homework problem, it just asks you to, I forgot, I think it probably just show you that, what's that? The product, the product of this thing is 0 or something. Okay, or actually it says that. Okay, I don't remember. But that's the meaning of this equation. Now that's actually a little bit important. Okay, you may not realize this right now. The reason is, if the magnetic moment, okay, so I use my finger here. If the magnetic moment is just rotating, of course I have the equation of motion. What's the meaning of equation of motion? Well, equation of motion just means that it describes the position of my magnetic moment at a given time. So that's the meaning of the equation of motion. So okay, so if I have this magnetic moment mu, okay, which is represented by my index finger here, I just actually move my finger like this, okay, or it doesn't matter which way I do, my finger is not shrinking. Okay, that's the point of this equation. But then you probably ask this question, right? You probably should ask this question. You say, under what situation actually this magnetic moment actually is not a constant? Actually, it will become a function of time, or actually you will reduce its magnitude. Well, okay. That answer is not far from today's lecture. That answer, in fact, you will see that in chapter 4. When we actually have those relaxation times added to this Bloch equation, then you're going to see an effect. And then actually it's not that easy to solve the Bloch equation. Okay? So, but that's not the content of today's lecture. Okay? But I just want to remind you, just give you an idea, say, okay, what's going on about this Bloch equation. Okay, so this is the most important part. Okay, so if you really understand the simple form of this Bloch equation, well, then actually you understand the complex forms. Okay, so this just show you. So if I take that differential equation, right, so I can write down like that. So d mu equals to gamma mu cross b dt. All right, why do I write down like that? Well, that's because I want to show you this picture, this drawing. Okay, so if I have a magnetic moment pointing this way, I have a field pointing this way, and that mu cross b gives me a direction going this way, right? So that's this big, bold arrow. Okay, so the d mu, that differential magnetic moment is going this way. And basically that says, okay, from that Bloch equation, this magnetic moment is going to rotate actually in a clockwise direction around this B field. Okay, so that is actually the meaning of this Bloch equation. Okay, now this rotation is called precession. Okay, just like in astronomy, how actually a planet precesses around the sun, for example, in our solar system. Okay, so you have this clockwise precession, and that's the first thing you can see from this Bloch equation. Okay. And that green ball, that just shows you an animation. Okay, so it's the same picture as this, but that's just an animation. That green ball is the magnetic moment, is that mu, or actually we call that spin. Okay, so it's going around this. That red arrow is my magnetic field. Okay, the next thing is, of course, then all of a sudden you say, oh, you see this Lamar frequency. Okay, so what is this Lamar frequency? Well, that Lamar frequency is actually, of course, it's the frequency for this spin or the proton, how fast for this proton to precess around the main field. Okay, and how do we actually get that? Omega. So I have the Lamar frequency, which is labeled by omega naught equals to gamma b. How do I get that? Well, okay. So the rest of this chapter 2 basically just shows you, okay, different ways to solve this Bloch equation. Okay, so after you solve the Bloch equation, actually you will see, oh yeah, I have a frequency term which shows me that is actually gamma times b. Okay, or so there are different ways to see that. And then the next bullet is about the phase. Okay, so what do we mean by phase? Well, phase is actually this portion here, because now what we are having here is, if I have say a proton, right? I have this magnetic moment mu. It precesses around the main field. Now you notice that actually this is actually we need to have at least a 2D trajectory to describe the motion of this moment. Okay. Now because of that, then you say, okay, now if I want to have a representation, mathematical representation of this motion, so I kind of project this whole thing on the plane, then how do I describe this? Well, okay, then basically I need to have two coordinate systems, right? Okay, so basically how to describe the trajectory of this circle, I need at least two coordinates. Or actually I can consider this, say, in a complex domain. So in a complex domain, then I have, okay, so then I say, okay, what's the magnitude and what's this angle? This angle is I always called phase. So that's the meaning of phase. Okay. Now this is actually a little bit important because this basically says in MRI we are dealing with complex signals. Okay. Because you actually have two components. We have two components actually we have to worry about. Okay. Now it's not this obvious. Okay, I have to also warn you here. It is not that obvious. Okay, not until in chapter 7 we'll show you how the MRI signal is going to be formed. Okay, so from that chapter actually you can really see, oh yes, there are two components left in the MRI, and then we describe them as a complex signal. But here it just gives you an idea. Say, okay, MRI signal is a complex signal, so then we describe this as magnitude and phase. Okay, and this is just a recap, right? Okay, so the gamma is the gyromagnetic ratio. So it's a little bit confusing. See, sometimes we say gyromagnetic ratio, we just refer to gamma. Sometimes we say gyromagnetic ratio, we refer that to gamma bar. And so you just have to be careful. What's the number people are telling you, but people normally will write it down, and then what's the unit? Okay, so if I really write it down as gamma bar, then I really say 42.58 megahertz per Tesla. Okay. All right, so then here are the ways to solve this Bloch equation. Okay, so again, the first line just recap the Bloch equation: d mu dt equals to gamma mu cross b. Now, the most easy case is that when the B field is pointing toward the z direction, okay, then you can sit down and then so you write down three equations, right? Because it's a cross product in a three-dimensional space. So you got three equations. You write down three equations, and with the B field being a constant field, well, okay, then you can find that, oh, the z component in fact does not change over time. The x component and the y component in fact looks like this. Okay, now when you solve this, all of a sudden you will find, of course, I don't have omega naught in the original Bloch equation, right? So what's this omega naught? So when you solve that differential equation, you will find that, oh, this omega naught in fact is that gamma times b, okay, in terms of the absolute value, in terms of the magnitude value. So omega naught is actually that gamma times b. So then this, and if you have a set of equations look like this, and this just tells you the spin is precise like that, and this gives you the frequency because that's the time from your differential equation. Okay, so this gives you the gamma b. And so this is one way to solve it. Okay, write down three equations and solve it. All right, so that's in one of your homework problems. And the other way is you can say, well, okay, I take that Bloch equation. Okay, I already kind of know I can easily solve the z component. So for the x and y component, I just rewrite that differential equation in terms of the x component plus the imaginary part of and with the y component. Okay, so just make the whole thing as a complex number. Or say vector. No, sorry, I guess I should not say vector. I guess I should just say number. And so it's a complex number. So basically, we can rewrite that Bloch equation in terms of this, something like this. Okay, so now you probably understand why I'm giving you this, question in your quiz. Okay, because you need to see this guy. And when you have this differential equation, now this mu plus is not a vector. This mu plus is just a complex number, look like that, but it's a function of time. Okay, so then the answer is actually this guy. Okay. And again, here you have this phase term. Because now I'm writing everything in terms of complex number. So complex number, I can write magnitude part and the phase part. And so this is the phase part. Phase part gives me minus omega not t. Okay. Now this minus sign is also important in this context, okay, because that minus sign means what? Minus sign actually in this case basically says the spin, or say the magnetic moment, is precessing actually it's precessing clockwise. So that's actually the meaning of that minus sign. Okay, because by mathematical definition, if I go counterclockwise, then the definition of my angle is positive. Okay, but if I go clockwise, then the definition of my phase gives me actually a minus sign. Okay, so that's the meaning of this minus sign. Okay, so this is the end of chapter 2. Okay, so any questions? No. Okay, so if you don't have question, then I'll just continue. Okay. Yeah, I think somebody asked me last time. So I don't have too many slides to show you. You probably noticed that. One slide I just go pretty slow, and then just tells you actually a lot of things. Okay, so this chapter 3. Okay, so maybe before I go into chapter 3, okay, so I'll just give you a general idea about this, why we are learning chapter 2, and then of course now we're going to learn chapter 3. In MRI, actually, we have 3 important magnetic fields. And the first one is actually the static field. That's the B naught we are just seeing there. Okay? So B naught is actually the main magnetic field. That's the 1.5 Tesla or 3 Tesla you have heard. So that's the major guy. Then the next guy in chapter 3 we are going to learn is actually what we call the RF field. Okay? And this RF field actually turns out to be has to resonate at this Raman frequency. Okay, now what's the meaning of that? So I'll tell you that. But this is the second important field we need to have in MRI. Now, in fact, with these 2 fields, if you have the main field and you have the frequency field, meaning that the RF field, then that already can give us the AMR. Okay, so these 2 fields already can say, okay, we can rely on these 2 fields and perform AMR experiments. So that's already important. Okay, AMR is not new. AMR, of course, has been, for how long? Since 1930 or 40. Okay, and then there is a third field. Okay, third field is the kind of the reason why Paul Lauterbur and Peter Mansfield actually received their Nobel Prize. The third field is the gradient field, okay? And we will not learn the gradient field until let's see, I think it's chapter 9, I believe. I think chapter 9 starting to talk about the 1D imaging, and then chapter 10 talks about the 3D imaging. So not until chapter 9 you will not encounter the gradient field. Okay, but literally actually from chapter 7 you will start to see why this gradient field actually that's important. Okay, why the gradient field actually provides the ability to do imaging. Okay, so wait until chapter 7. You will see. If you can realize that, that's great. Okay, and then you're as good as Lauterbur. Okay, so in this chapter 3, actually the focus now is more about the RF field. The radio frequency field. Okay, so again, here are the 5 important bullets where I'm going to talk about. Okay, the first one is the equation of motion in the rotating frame. Okay, and then the second thing is that, okay, so then what's a rotating frame, right? So then we have to tell you what's the difference between the rotating frame and the laboratory frame. And then because of that, we have to consider what we call the effective field, because in the rotating frame, things have changed. The way the way we measure the fields, the way we measure fields will be the same, but the measured fields actually will be different. So as we say, the effective field. Okay, and then what's the meaning of that phrase, unrandomness? Okay, and then the last one is what is the meaning of this RF transmit coil. Okay, so to start with, the first thing that we have to talk about this rotating frame. Okay, now why we discuss this? That's because if everything is static means that if I just have a B field pointing this way, even if I just change in this B field, just along this direction and changing this magnitude of this B field as a function of time, that doesn't help. Okay, and if I just have this one field, doesn't matter what I do, then the spin, of course, say the proton, okay, or say the magnetic moment, is just going to be precess around. Say, okay, here is my main field. Okay, so the proton is just going to precess around this main field. So it doesn't matter what I do, it's going to end up with like that. So I need a second field. Okay, so I need a second field, and in order to bring in this second field, so we would say, okay, try to do something, right? So one thing you can imagine is you say, well, okay, then maybe we will start to actually rotate the field. Okay, but there is actually a reason behind this rotation, and that is actually from this Lamar equation. It is actually from that precession, because naturally, if I have a main field pointing this way, say just 1 Tesla, I have a main field pointing this way, I have a spin, okay, a proton precess around this main field, and what is actually the frequency you will precess around this main field? Well, the answer is is that gyromagnetic ratio. So if I have 1 Tesla main field and the precession, I mean this Lamar frequency, meaning that the inverse of the precessing rate is in fact is 42 megahertz. Okay, so you know that. So in fact, it's also because of that. So we have to consider this rotating frame. Okay, so in this chapter 3, and I think all the way until I forgot in which chapter, either chapter 7 or chapter 8, we actually use this notation. So you will see that actually a prime. In all the equations, you will see there. Okay, so in the second bullet, you see a prime in that equation. Okay, that prime does not mean derivative here. That prime is just a label. That prime just says, okay, I consider that equation, I consider the evaluation of that equation in the rotating frame. Okay, so the first guy is the d mu dt on the left side of the equation. That just basically says the equation, or say the measurement I'm going to perform in the laboratory frame. Okay, so laboratory frame simply means that the frame, we're sitting here, we're not moving, we're just watching this thing. Okay, so that's the frame we are. Really assume that we're not moving. And the prime system, the one labeled with prime, is the moving frame, is the rotating frame. Meaning what? Meaning, so I have to stand here, right? Meaning that, okay, suppose I'm rotating myself. Okay, you guys are watching me, right? Okay, so I'm rotating myself like this, and from you, actually, of course, you say I'm rotating, right? But if somebody actually stands, say I have a little rat on my hand, right? So if I just move like this, that rat look at me, that rat will say I look at that rat, right? Then I will not see that rat is moving, because to me that rat is always actually at my front. Okay, so I just look at this. I say in my frame, I'm in the rotating frame, but when I look at this rat is not moving. It's always at my front. But to you, okay, you are sitting in the laboratory frame, and you look at that rat, you say, okay, that rat is moving. So that's the difference between the laboratory frame and the rotating frame. Now, because of this, so mathematically you can say, okay, so there's a difference between these two frames, and mathematically you can relate these two frames by considering this rotation. Okay, so that's that big omega. Okay, that omega in fact is a vector. Okay, so I look at the book. The book basically says it's angular velocity. I think that's the way it says. Okay, and frankly, I guess I don't like that name. You know why? When I look at that equation, I say, oh, what is actually the unit of that capital omega? Well, the unit of that capital omega, in fact, is the inverse of time. So it's a frequency. So if I really want to call that capital omega, I really want to call that actually a frequency vector. And so that because the unit is frequency. So that's probably what I would prefer to call it. Okay. All right. So okay. So I'm not going to go through that. I mean, I think it's a one-page derivation in the book. Basically shows you what is the mathematical relation between the two frames, which is linked by that capital omega. You know, whether you call that angular velocity or call that frequency vector, it doesn't matter. It's linked by that. Okay, and then you can derive. So just in a very general form, you have the laboratory frame, you have the rotating frame. So one guy is rotating. You can write down the relation between the two frames, just like the second bullet showing you. So d mu dt equals to d mu dt prime plus actually omega cross mu. Okay, so this is a very general form. And now the problem is this, because of that, so as I mentioned, now if I want to do a measurement of my B field, okay, now I just have one B field, okay, so I have this main B field, and I want to do a measurement, and so in the laboratory frame, the B field is just that bold B, okay, so it's a B with a vector. But then in the rotating frame, when I measure this B field, then I'm getting, in fact, what we call the effective field. So it becomes this B effective. That is actually the bold B plus this capital omega divided by gamma. Okay, and that gamma there is because that is actually because of this mu, because of the magnetic moment, okay, because of the field we apply. Okay, so okay, so yeah, I think actually this probably don't like this way. All right, so now we have to say, okay, now we will bring in this second field, what I call the radio frequency field, the RF field. Okay, so why is that? Okay, now let's look at actually the third bullets. Okay, so that's the major thing I want to tell you. So if I just have this one main field, and even if I bring in the second field, so let's say this is my main field. Okay, now I bring in actually the second field. But if this second field, in fact, it's just another static field. Okay, so basically you say, well, okay, so what? I mean, I have two vectors, and of course you always just add the vector sum of the two vectors, so you get the overall. So I say one field pointing this way, the other field pointing this way. Okay, never mind about the magnitude of each field. So I get a vector sum pointing this way, and my proton is going to just precess around the overall field. Okay, so that's it. You know, nothing is going to happen. So that's just as good as if I have the original field pointing this way. So nothing is going to happen. So I need to bring in this second field, this RF field, to do what? To do something actually different. Okay, so I want this RF field to, say, precess at the Lambda frequency. Okay, why is that? Well, okay, so think about this for a minute. Okay, so I have the main field pointing this way. I have my proton precess like that. Okay, so we are now all sitting in the laboratory frame, and I look at this little proton, it precesses just like that. Okay, but imagine, put yourself with that proton, okay? So if now, okay, again, I move to here, okay? So if the proton precesses like this, and at the same time, actually, say I or you also precess like this, right, at the same rate, okay? So if I just do that, well, what do I see? I actually see a static field. I see a static proton. Proton is not moving if I rotate at the same rate as this proton. Okay, just like I said, okay, if I have a rat in my hand and this rat is moving with me, then this rat is not moving to me, the rat is not moving, the rat is moving to you. Okay, so same thing, if I have a proton precess like that, then, and I move at the same rate, then this rate has to be the this Lama frequency, okay, because this proton by nature is going to precess at the Lama frequency. And so if I move at that frequency, then that proton is not moving from my perspective. So I have designed, so because of that, and I want to kind of say, okay, I want to put this proton in a frame such that it is not precessing. Okay, so because of that purpose, well, okay, then you probably ask, why we are doing that. Well, okay, there are some convenience later on, when we consider certain things, and so this is just from the convenient point of view we do this. Okay, so you say, well, okay, so now, okay, but sorry, actually that's not completely true. Okay, I'm just saying that from the mathematical point of view, actually it's this, but from the physics point of view, okay, I will tell you more later. I mean, say 10 minutes later, you will see why this is important. So I want to design my RF frequency coil, such that it resonance. Okay, so one way to say is, one technical way to say is, I need this RF coil to resonate at the Lama frequency. Okay, resonate at the Lama frequency. Okay, so in other words, I want this RF coil somehow when I'm in that frame, when I'm kind of somehow I can see the proton as if the proton is not moving. So that's kind of the purpose for this RF coil. Okay, so that's kind of the first thing, the idea we want that. Okay. And okay, so now the first bullet is just saying that this RF field is the so-called B1 field. Okay, so I got to separate two things here. Okay, I'm saying one thing. Okay, so I was saying that I want this RF coil to resonate at the Lama frequency. Okay, that just means I want to design the coil such that I can be in the rotating frame. Okay, but then I haven't done anything to the spin yet. Okay, so the first thing is that we are, because of this RF coil, we are in the rotating frame and with that proton. Okay, so now if somehow I'm one of the electrons, and and I look at this proton, okay, then actually that proton is not moving. Okay, but we haven't done anything to that proton. The second thing is that this RF coil, in fact, will also produce a field, okay, a magnitude of field, I should say, and that magnitude of the field is called the B1 field. Okay, so sometimes if you hear people say the B1 field, that represents the RF field in MRI, or in MR, actually it's kind of the same thing. And this is called the transmit coil. Okay, now why it is called the transmit coil? That's because we are using this RF coil and we are going to do something to this spin. Okay, in fact, we are going to rotate this spin. So because of that, because we are going to rotate this spin, so we call that a transmit coil. Okay, Now later in chapter 7, actually, we will talk about the receive coil. Okay. Now guess what? Actually, physically you say, well, it's the same coil. Okay. The electronics actually are different, but physically you say, oh, it's the same coil. Okay, but it's not. Actually, it's two different sets of electronics. Okay. But for now, actually, we are talking about the transmitting coil. Okay, and then the last bullet I kind of covered that. Okay, so just because we want in this rotating frame, we want to see a static spin, so that's why we want this RF coil to resonate at the Lama frequency. So in other words, RF field rotates at the Lama frequency. Okay, that's kind of a very, very strange way to say it, but that's actually the meaning is that way. Okay, so now we're talking about what is actually the say the field strength from an RF coil. Okay, so the first guy actually we can think about is, okay, we have a linearly polarized B1 field. Okay, so let's write down the mathematical representation. So you say, okay, it's this B1. B1 is the magnitude of the field, and then I have this cosine omega t, and x is just moving along the x direction. Okay, so okay, now what does this mean? All right, again, we are looking at this actually in the laboratory frame. So we are looking at that field in the laboratory frame. So we are writing down that equation in the laboratory frame. Okay, B1 cosine omega t and along the x direction. Okay, so think about that for a minute. So when the cosine omega t equals to 1, then of course I have the maximum magnitude of this field B1. Okay, so particularly of course when t is equal to 0, so meaning that at the very beginning, so say, okay, so I'm going to turn on this RF field. Okay, so right at that moment, and the magnitude of this B1 field is B1. Okay, now of course now it depends on what is the value of that omega I'm going to assign, or say with all the combinations of electronic components, how am I going to actually design my coil such that I can change that frequency. Okay, so that's what I mean. There are two things. One is the magnitude of the field, which we call that B1. The other guy is that omega. That's the frequency of this coil, or of this field actually. And that frequency, in fact, you want that frequency to be the Lama frequency. So that omega there, in fact, will become your gamma times B naught. Okay, so that's so from the laboratory frame, that field basically is an oscillating field, but it's a linear field because it's always pointing along the x direction or minus x direction. Doesn't matter. Okay, so it's just toward the x direction. And now you can say, well, okay, so in the laboratory frame, that's what we see. It's just oscillating like that. But I want to rewrite that field in the rotating frame. Okay, so now it involves actually a rotation of my frame. So I have to write my x direction. So x direction is in the laboratory frame, and x prime direction is in the rotating frame. Okay, and they are basically off by this. They are related actually by these two equations. Okay, again, now here I have to be a little bit careful. Okay, so here actually, of course, this omega should be the capital omega. Okay, but now I just say, okay, if I assign that capital omega to be the same omega, I mean in the linear field, so meaning that I design my RF coil such that the frequency resonates at that capital omega in the rotating frame. Okay, so now, going through this little, say, math, then I can rewrite this field, B1 field, in the in the laboratory frame in terms of the field in the rotating frame. Okay, now after So this is the representation, the mathematical representation of the same field, but viewed or say measured in the rotating frame. So it's like this. Okay, now be careful. There's a factor 2 here, factor half here. Okay, so now you know that if I want to measure the field, meaning that I measure the field through time, I mean as a basically average the field over time, then this term is gone, right? Average over a sine function, average over cosine function, this term is gone. So what I have left is actually B1 over B1 divided by 2 in the rotating frame. So in the rotating frame, if I do the measurement of this field, all of a sudden I find that, oh, okay, I'm not getting actually the B1 field, I'm getting B1 divided by 2. So meaning that the magnitude of this field, in fact, is reduced by half. So this RF field, in fact, is less efficient. Okay, so that's the kind of the meaning of this section about the linear field. Okay. Any questions? Sure. This whole thing? Okay, from the very beginning? Okay. All right, okay. So but okay, let me ask: is it clear that about the rotating frame and the laboratory frame? That's clear. Okay, so is it clear the purpose of having this field? First of all, one purpose is to make sure the proton in the rotating field, in fact, is not moving. I mean, at the very beginning, it's not moving until I apply the RF field. Okay, so as a first example, so in the textbook, okay, if you go to the textbook, you will see the first example. The textbook shows you the linear RF field, and the linear field. Okay, again, so what do we mean by the linear field, right? So this is again, it's a new terminology. The linear field is just defined by this. So in terms of the mathematical representation, it's equal to B1 times cosine omega t, and then with a vector pointing to the x direction. But we are viewing this, okay, the important part is that we are viewing this field actually right now in the laboratory frame, meaning that just like where we are, we sit there and we watch this guy. So that mathematical equation basically tells us it's a field. So if this is the x direction, this is just say, okay, at t equals to 0, that field is B1 pointing, say, this direction. When omega t, okay, doesn't matter about the frequency, but let's say omega t equals to pi over 2, well, there's no field, right? When omega t equals to, say, pi, well, then that field becomes pointing this way. Still, the magnitude is B1, but now it's pointing to the minus x direction. So as a function of time, this field is just oscillating along the, say, this x direction. All right. But again, we are just viewing this actually in the laboratory. I'm sorry. Yes, in the laboratory frame. Okay. So it's just moving like that. Okay. But we are interested in viewing this field in the rotating frame because there is, again, as I said, from the mathematical point of view, there is an advantage to do this way. But from the physics point of view, actually, it's far more important. Okay, but from the physics point of view, that's something I'm going to tell you maybe 10 minutes from now. Okay, why we have to do this. So mathematically, you say, okay, how am I going to view this in the rotating frame? All right. So the first thing is I have to rewrite that x direction and also the y direction. Okay, these are the x unit vector, y unit vector. I have to rewrite these two unit vectors in terms of x prime and y prime. Now, x prime and y prime are the unit vectors in the rotating frame. So I got two frames here. Okay, this is the laboratory frame. This is the rotating frame. This frame is described by unit vector x and y. This frame is described by unit vectors x prime and y prime. The difference is this frame is not moving, this frame is rotating. So in terms of mathematical format, I can write down the relations between these 4 unit vectors like that. So this is the way to describe the relation between these 2 frames. Okay, now your question may be, okay, how can I write down this set of equations? Well, this is no magic. This is just like, imagine that you rotate, okay, so if I go backwards. Okay, here. So see, so if I have a frame, actually this one is better, okay? So you see, if I rotate, if the z direction is equal to the z prime direction, I rotate the frame like this. So this is just like, oh, you have a unit vector going this way. You can just decompose that unit vector in terms of x and y. Okay. Same thing if you say, consider I want to decompose the x vector in terms of x prime and y prime, x prime and y prime. You can do that too. Okay. So there's no magic. It's just from there. Okay. Now, if you have a 3D rotation, then of course that's more complicated. Then you got the Euler angle involving all that stuff. Okay. All right. So you can have actually 2 equations like this, and then I take the original linear field, which is this guy. It's a vector, by the way, and it's a function of time. I rewrite that in terms of this. Okay. Of course, then you have to use your trig functions, trig identities. Okay, so that's why those things are in your quiz. And then you got this one. Now this is actually the same field, but you are viewing the same field in the rotating frame. The next thing is, then of course you say, well, I want to measure this field in the rotating frame. Okay, so the usual way to measure say a changing field in the rotating frame is that then you are going to calculate, basically you are going to average the field over time. So when you do the averaging, you got this sine function, but if you integrate from basically say omega t basically changes from 0 to 2 pi, well, you do that average, you find that it gives you a 0 field. The average field is a 0 field, right? You have sine cosine function oscillating, you calculate the average, that's 0. The only thing will be left is because this guy. You have actually still have a 1 there. Okay, so the magnitude of this field in the rotating frame becomes b1 divided by 2. And so then the meaning here, okay, so this is just the mathematical derivation. Okay, so what's the meaning after this mathematical derivation? It means that your RF field in the rotating frame is effectively reduced by half. Okay, now that's a bad thing because it means that in order to generate that field from a coil, you have to put in a current. So then you can generate a field. But okay, so say, okay, I put this much current, I generate a field B1, but then effectively it looks like actually a B1 divided by 2, that the field, is reduced by half. It means that if I still want a B1 field, okay, a magnitude B1 field means what? I have to double my current. Okay, so that's a bad thing from just from the matter whether you are looking at this from physics point of view, engineering point of view, it's just bad. So you don't want to do that. Okay, so that's why here we say the linear field is not effective in the rotating frame. Okay, I think there is such a remark in the book. Okay, so that's what you have to realize. So is it clear now, or okay? Yeah, just feel free to ask. Okay, so you go home, you think about it, and then next class if you say, okay, it is still not clear, all right, just bring up the question again. Okay, that's perfectly fine, and that's why we have to explain. Okay, now let's look at what we call the quadrature coil. Okay, what do we mean by the quadrature coil? Quadrature coil is, in fact, now I really want to have a B1 field in the rotating frame. Okay, so we write this as B1 and then the x prime direction, unit vector x prime. So I really want a B1 field in the rotating frame. So then what is that representation in the laboratory frame? Okay, that representation becomes this. Oh, sorry, you know what? Made a mistake. I should have B1 here. I should also have B1 there. Right? Okay, so you look at this. You look at this equation with B1 as the magnitude in front of it. This means what? Okay, so if you think about it, now I got the xy plane, right? So when the time equals to 0, I have a B1 field pointing to the x direction. But when omega t is actually, say, pi over 2, then what do I have? Okay, then I have the B1 field pointing to the minus y direction, right? Now you keep increasing your time such that omega t equals to pi, then now the B1 field in the laboratory frame is now pointing to the x direction, and now keep increasing your time. At some point, when omega t is actually 3 pi over 2, then your field is pointing to the plus y direction. Okay, so now you can imagine what is this field doing in the laboratory frame that we are seeing. This field, in fact, is rotating like this. Okay, and the magnitude of this field is B1. So this is what I mean. There are two things. Okay, one is that you have the magnitude of the field. The other thing is that this field is also rotating. But how are you going to make this field rotating from this RF coil? Well, okay, so the technical term is to say you have to resonate your coil at that frequency omega. Okay, you have to design that coil with a resonant frequency omega. Okay. Now, typically, I mean, for those who are from, say, engineering with an engineering background, or especially in electrical engineering background, if you have a coil, just a simple circular loop coil. If you have a circular loop and you put say a capacitance of this coil, okay, well, then in fact, then basically this coil, not only the capacitance, actually we also need the inductance. Okay, so let's say with a circular loop, if you put a capacitor and an inductor on this loop, then this loop is going to resonate at a particular frequency, and that frequency, in fact, is what? Is actually 1 over square root of L times C. Okay, L is the inductance, C is the capacitance. Okay, so naturally, if you say, okay, I don't put an inductor because the wire itself also is a piece of inductor. It has the inductance, okay, although very small, but that's fine. It depends on actually the frequency you want. So if you just say, okay, take a circular loop, and the inductance, if you know how to calculate, in fact, that can be calculated, okay, and so you calculate the inductance, and you put a capacitor there, and again, your natural frequency of this circular loop is still the same formula, 1 over square root of L times C, except that right now L is actually just the inductance of this loop, and C is the capacitor, whatever capacitor you are going to add in there. Okay, and this is actually the trivial coil you can have in MRI. And you can actually use that coil later. You can use this coil. Now, if you have seen people image eyes, okay, or a flex coil, that is, my understanding is that is just a simple circular loop. Okay, and guess what? A company, is going to sell you, I think, maybe $10,000 for that loop, for that single wire, okay, for that circular wire. Okay, so the next remark is just to tell you that the quadrature coil, and this is the reason we are calling this a quadrature coil, is just because it's rotating like this in the laboratory frame. Okay, actually another word to say this laboratory frame is the resting frame. Okay, but doesn't matter. It's just a name. In the laboratory frame, it looks like this, so we call that quadrature core. Quadrature just means that going to different two directions, so we call that quadrature. So the quadrature coil is more efficient actually in the rotating frame. Okay, so now back to the the horrible Bloch equation, right? I guess it's not that horrible at this point. So the first bullet just tells you the equation of motion, which describes the spin. Now, in fact, we write that in terms of gamma mu cross product with the B effective. Okay. Now you may remember the B effective. At the very beginning, I show you B effective is just B naught plus capital omega divided by gamma. Okay. But now, because I'm adding the RF field, I'm adding that B1 field, so all of a sudden, I have this B1 component in there. And then when we write it out, actually we have this whole thing. We have omega naught. Omega naught is my famous Lamar frequency, gamma times B naught. Okay, B naught is the static field. That does not change. And so I have omega naught minus omega, and then it's along the Z prime direction. Okay, again, Z prime in this case, in fact, is Z, but we write Z prime just to say that we are in the rotating frame. And then plus omega 1 X prime. Okay. Now I have to be careful. What is omega 1, right? I haven't told you what is omega 1. Okay, omega 1 is just actually nothing funny. Omega 1 is just gamma times B1. Okay, now what is that? Okay, so from one simple example, okay, if you think about the following way. So let's say, I think later I probably will show you this animation. So let's say I have this proton in the in this rotating frame, okay, and I'm now actually somehow I'm in the rotating frame, so I'm not seeing the motion of this proton until I have that B1 field. Okay, but this B1 field, what is that B1 field going to do in the rotating frame? So in the rotating frame, if I only see the B1 field, say the B1 field going this way, well, okay, then this proton, from my perspective, this proton is going to precess around this B1 field. Okay, and again, you have to be careful. Say, okay, this proton is going to precess actually clockwise around this field. Okay, so which way it's clockwise? I think it's this way. Okay, so this proton is going to precess around this B1 field like that in a clockwise direction. So because of that, and it's proton, okay, so this gyromagnetic ratio basically is a constant for, okay, so different species actually have different gyromagnetic ratio. So for proton, again, you just have the same gamma, which is 42.58 megahertz per Tesla. So for that omega 1, okay, so that's one simple way to say, okay, why that omega 1 is again defined as gamma times B1, because we are talking about proton, and even in the rotating frame, I have this B1 field. The resonant frequency, or say the precession frequency for the proton is just actually gamma times B1. So that's one simple way to look at it. Okay, so, but there is actually, there's another thing actually I have to tell you. So we have the mathematical representation from the first line. Okay, so I have omega naught minus omega, and that's along the Z prime direction. And then I have the B1 field actually along the X prime direction. Okay, so the important part is this. So if I have omega naught equal to omega, then I don't have the frequency along the z prime component, meaning that in the rotating frame, I will just see the component along the x prime direction. Okay. Okay. Now in this case, actually there is a special name which is called the unrandomness. Okay, meaning that omega equals to omega naught. Okay. Now that omega, this omega there. Okay. Remember that omega is the capital omega from the capital omega that describes how fast actually the frame is moving. Okay. So that can be a little bit different from the omega naught. Okay, so what does that mean physically? Okay, so now here is the answer to the question 10 minutes ago. What is the physical meaning? The physical meaning is this. Okay, so again I have to move myself to here. So imagine the following. Now I say, hey, I have this rat in my hand, right? And this I'm rotating like this, and I see this rat, just as if I'm not rotating. But imagine the following. I'm rotating at one speed, okay, and but this rat, so my hand, or let's say my hand, actually is moving at a different frequency, okay. So it's a little bit like this. All right. So after several cycles, then of course, what do I see in my frame, from my perspective? Oh, I see, yeah, the microphone. So from my perspective, what's happening to this rat? From my perspective, even though I'm rotating, I am seeing this rat or my hand actually moving like this, slowly, okay? Because there is a little bit offset between that omega naught and omega. So that's why I'm seeing. Okay, so you say, now why this is important in MRI, why I call this actually important thing. The important part is this. If I don't have the same frequency, I mean, say, okay, the proton is precessing this way, and then I design my resonant, my RF coil resonating at a different frequency. So it's like, the phenomena I just gave to you. Okay, I'm rotating at one frequency. This rat is moving at a different frequency. Then I try to acquire my data later. Okay, right now, of course, you don't know this, right? So not until chapter 7, you don't know how we are going to acquire the data. So if I don't have the same frequency, meaning that omega naught is not omega, then later you will find that you are going to lose signal. You are going to lose MR signal. So that's the important part from physics. So in order to have actually a good signal from MRI, or even actually for NMR for that purpose, we prefer to have omega naught equal to omega. Okay. So that's why people will say, okay, the on-randomness condition is important. If you don't have that, then it's called the off-randomness condition. Then typically you will lose your signal. Okay. Now, it's actually, of course, now if you think a little bit more, right, you say, okay, this is actually a little bit complicated. Okay, not as easy as I just described to you. So imagine the following. If you have a uniform sample, you do the MR experiment, do MR measurements, or you do MRI measurements, doesn't matter. You have a uniform sample. Then what I described, of course, is true. But what's happening if in this sample I have a heterogeneous material, and which of course is true, right? Even for our body, for our brain or our body parts, for most of the stuff. In fact, you do have heterogeneous material in there. So then you say, well, okay, now you got a problem, right? Because how are you going? So what frequency are you going to match? Because we are having actually different materials in there. Well, okay, not that bad, right? You say, well, okay, not that bad because most materials we are consider are compositions of protons. So it's not that bad. The frequency, yes, it's going to be a little bit off, and it's off by a little bit, not much. And that is actually, of course, the chemical shift. Later on, okay, now chemical shift, okay, you won't learn that until chapter 17. So that's a little bit chemical shift you will see, okay, or actually, of course, even later, in chapter 25, then that will be the susceptibility effect. That's part of the reason, okay. There can be other problems as well. So let's say if you have a bad coil, okay, but in this case, your coil is not going to be off-run by, say, so much frequency, okay. So let's say on 1.5 Tesla, you want 63 megahertz, and your coil is not going to resonate at, say, 60 megahertz. Okay, if you are off by more than 1 megahertz, that's a bad coil. You're not going to get signal from that coil. Okay, then you have to call the manufacturer and say, all right, you have to fix that coil. And normally, I just gave you the tip, right? So how do you think that they fix that coil? Anybody? No, that's the solenoid coil you are thinking. But I was just giving you guys actually a quick example, how do we get a random frequency of just even a circular coil, right? Huh? Right. So okay, so if the coil does not resonate at the Raman frequency I want, then what am I going to do with the coil? Yep, change the capacitor. And then they send you a bill, for another, you guess what, $10,000 maybe. Okay, so and then the bad news is that you cannot open it up and change that yourself, right? Because if you do that, you avoid the warranty, and then you buy a new coil. Okay, so all right, now this the third bullet. Okay, so basically, right now we are just kind of talking about the constant field, right? Okay, so that B1 field. Okay, so if this B1 field, now be very careful. This B1 field is a constant field in the rotating frame. Okay, so I wrote B1 x prime, and so B1 field is a constant field. Then as I described earlier, I have, so let's say this is my B1 field going this way in the rotating frame, and I have the proton here, and in this rotating frame, if I'm having this unresonance frequency condition, okay, I should say unresonance condition, then I'm not seeing this field, the major field, along that direction. Okay, so this proton will just basically say, okay, it just sees the B1 field in the rotating frame, and so in the rotating frame, this proton will just precess in the clockwise direction, just precess like that. So of course it goes by an angle, right? From this perspective, there is an angle, and so what is that angle? Well, of course, we just kind of solve that Bloch equation in chapter 2. Okay, so that's your homework problem, right? You are going to solve that Bloch equation in chapter 2. And what is that phase? If you remember, that phase is omega times t. But for the RF field in the rotating frame, what is that omega? That omega is actually this omega 1 is my gamma B1. And what is the time? Well, time is actually how long you are going to turn on this RF coil, this RF pulse. Okay, so that time is normally labeled. Well, okay, it depends, but here we just say, okay, the duration of this on time of the RF coil is tau. So this angle, okay, even though we call that flip angle, but it's the same concept as we have described in chapter 2. It's all from the Bloch equation. So we have the precession, okay, and this is the phase. And that phase just gives me omega 1 times tau, and omega 1 is gamma times B1, and then times tau. So this is actually my angle. Okay. Now, of course, you make this a little bit more complicated. You say, well, okay, if this B1 is not a constant, if this B1 is also a function of time, okay, so you just make this more complicated, then you basically just create what we call the RF pulse. Well, no, actually, originally that B1 is the RF pulse. I mean, what do we mean by the pulse? Pulse just means that I turn on this field for some time and I turn it off. Okay? So later on, you will hear this terminology RF pulse in later chapters. But so that's kind of my RF pulse. So once I have this B1 field turning on and turning off, and what is actually the angle, and that angle basically is the angle I rotate the spins, because originally if I have the main field going this way, all the spins are going this way. Now with this RF field, I have the RF field pointing toward the X prime direction in the rotating frame. I have now all these protons actually rotating this direction. And this angle, okay, between here and here, this angle is described by this equation. But this is no different than how you are going to solve your Bloch equation. Okay, so then if you look at section 3.3.2, okay, so then of course the Bloch equation basically is, a different Bloch equation tells you, okay, what's the position of the spins in the rotating frame. Okay. Now in the laboratory frame, of course, this spin is going to be more complicated. Okay, so I think this animation shows you that. So this is actually in the laboratory frame. Okay, and then you can see the trajectory is going to look at so complicated, because on one hand the proton has to precess around the main field, right? But then on the other hand, because you have this B1 field, actually remember this B1 field is rotating around the main field, so then this spin on one hand it's tipping onto this XY plane, but on the other hand it will also has to be, the direction is switched by the rotating B1 field. Okay, so this blue arrow representing the rotating B1 field. Okay, and then now if I put ourselves in the rotating frame, then this green ball, which shows me the spin in the just a spin, but we are viewing this actually in the rotating frame. So you see that, this spin just precessing around this B1 field very nicely, cleanly. Okay, let's say that. And so this is actually the trajectory you see in the book. Okay, but if you put yourself in the laboratory frame, this is the trajectory you are going to see. It's so complicated, and that's the animation. Okay, now how are we going to detect this? Why are we tipping the spins? The point is to detect the presence of these spins. Okay, and then we will talk about that actually in chapter 7, how we are going to detect the signal, whether it's an MR signal or NMR signal. It's actually the same. Okay, so I think I have those. Okay, now this is just kind of to say, look at the problem, okay, from another angle. So the first bullet just shows you that, okay, this X prime direction in the rotating field is actually efficient. Okay, so then you basically say, okay, rewrote that in terms of this in the laboratory frame. And now, and that's what we call this, I think what they call this the left circularly polarized coil, okay, because of that minus sign. Now, if you say, okay, what's going to happen if I consider a plus sign between those two fields, or say two directions? If I have a plus sign, well, guess what? Then when I have that in the laboratory frame, and I rewrite that in the rotating frame, meaning I rewrite that in terms of x prime and y prime, well, guess what? It's this. Okay, so then this is really bad news, right? Because if I want to measure this field in the rotating frame, and again, we just average over time, that just gives me a zero field. So it said, basically, so the point is, if I have a right circularly polarized field, well, guess what? That is completely inefficient, because that field is doing nothing to the spin in this laboratory frame. Okay, so I think this is the last slide. Okay, so before you guys overloaded. Okay, so the last slide, I just want to say this is actually the homework problem you are going to have. Okay, and then okay, so in this case, actually, yeah, I think they were talking about the off-randomness condition, so meaning that omega now is not omega. So you see that, okay, now you got something like this, okay, complicated, and it asks you to, I think, figure out equation 3 to derive actually equation 3.54. Okay, now what I want to tell you here is I just tell you there of course there are hints in that homework problem. I think that's the last homework problem in chapter 3. So there is a hint in there, but you can follow that hint. Okay, I don't like that hint. Okay, and there is actually a better way and a much quicker way to solve the problem. Okay, and my hint to you is this: you just have to actually look at this picture, which you do have that in your textbook. Just look at this picture closely. Okay, look at this picture more carefully, and then you will realize actually there is a quick way a high school student can solve it. Okay, so you don't really need something too complicated. Okay, so let's just quickly review what the important points we learned from this. Okay, so here the important points we learned from this chapter 3 is the equation of motion in the rotating frame. So we have the subprime representing the rotating frame, the Bloch equation. Okay, and then I explain what's a rotating frame, what's a laboratory frame, and then what's the meaning of the round randomness, and what's the meaning of the transmit coil, okay, and also the effective field, and go to the chapter 2. Okay, so these are what we learned. So the Bloch equation, we learned the Bloch equation, how to derive the Bloch equation with 3 important equations. Okay, and then what's the meaning of phase, and the MRI signal is a complex signal, and MR signal is also a complex signal, and the Lamar equation, okay, because in the gyromagnetic ratio, because we have the field, and these are just the natural thing, and then how to solve the Bloch equation. Okay, so you have different way. You can use really break this in terms of Cartesian coordinates to solve the Bloch equation, or you can rewrite the Bloch equation in terms of a complex notation, solve that way. Okay, precession. Okay, the spins, the proton actually precess around the field in a clockwise direction, and also what's the terminology of gyromagnetic ratio. So that's what we have talked about today. Okay, so any questions? Okay, so yeah, go home and digest and do the homework problem, and if you have questions, and you can ask on Thursday.